Okay, before we continue on with the geometry, we must go back a little bit to the algebra. And you'll see that you're going back to the algebra for this reason. They're the same thing. So let's just look at how we're going to go about learning to slide vectors, right, through the origin so that we can, in other words, slide them across their direction. I'm going to go ahead and draw this one up at around 15 degrees here so that we can determine both their slope-intercept and, more importantly, this offset distance here. Because we know that in all reality we can only slide vectors off their line if we replace them by an equal vector but then also a moment. And in this case you see the moment is negative because it is counterclockwise. So we will start talking about coordinate systems and defining them. We'll call this for now an x and a z. We're going to call this the right hand coordinate system, and we'll talk about now what in fact we need to know to get the equation of a line. In all reality, we do not need to know the magnitude of the force. We just need to know its point of application and then the x, y, and z coordinates of the point. In this case, of course, we're saying that y is 0. So let's assume for now that this angle here equals 15 degrees. You could have gotten that any number of ways. And how do we then go about calculating both the slope-intercept and the offset distance through the origin? Well, you do it first and foremost by learning to slide vectors across. I'm sorry, we're going to call this swiping vectors. Sorry. Sliding is along the line, swiping is across. So you need to know that you get the geometry of the forces from the geometry of the structure, if you would. So in this case, we'll make an assumption here, if my marker will pick up, that we're going to guess that that's 2 in the x and 1, 2, 3, and 4 in the z. So we're going to say that point is 2, 0, 4, and we're going to ask what is its intercept along this line and what is its offset distance. Now notice I'm throwing you probably with the z, but we do want to start at least being able to think that we can think in a different plane than the xy plane. So in this case the slope would be not the change in x, change in y over the change in x, but the change in z over the change in x. So let's write that. First off, our slope is going to be 4 divided by 2. I'm sorry, that's not the slope. The slope is going to be the tangent of 15 degrees. In other words, the slope of this is also known as the tangent. That becomes incredibly important to remember that the slope and the tangent are the same thing when you're trying to mix between the worlds of geometry and algebra and matrix algebra, which in fact is what structures and strength of materials essentially is. And so what then is the equation of the line of force? Well, you just do it this way. You remember that it's z minus z1 over x minus x1 equals slope. That's essentially the point slope form, if you would. And so in this case, you're going to say it's z minus 4 over x minus 2 all equals the tangent of 15 degrees. Now, doing stuff like this is where, in fact, you eventually memorize not only the 0.2588 and the 0.9659, but also the radical forms all the way down to the tangent of 15 degrees. And it's worthwhile doing. We're not going to do it here, but you can realize you end up with a slope here of, or an equation that looks like this: z minus 4 equals the tangent of 15 times x minus 2. And if you want, you can more or less decide that you want to do this in the y equals mx plus b format, so you can kind of go through here and calculate this out as z equals the tangent of 15 times x plus 4 minus the tangent of 15, times 2. This being your slope-intercept, and this being your slope, which we knew it was because it was from the start. Now, if you want to know the tangent of 15, you can do it a couple of ways. You can know that it is pretty close to the tangent is the same as the sine, which is pi over 12. So a little bit off. We said that's off by 4%, but this concept here will in fact get you the slope-intercept, and then what you finally have to know that is the offset distance is going to be the slope-intercept. See if I can go to a new file, new thing here. Not going to let me. It's not liking that, so I'm going to stop this now and see if it finishes up. But you want to remember that it is insert, home. Home is a new slide, a blank new slide. You want to remember that the offset distance through the origin is equal to the slope-intercept times the cosine of the angle of the line, the direction of the line. And you'll see that later, that becomes the way to test that is, in fact, if you have a line that is parallel with the x-axis, obviously the angle is 0, the cosine of 0 equals 1, and therefore you get the full distance. As it's less, the cosine goes down, and so that distance will always be less. But you want to remember that to offset a line through the origin, you want to play around and get some good intuition with this one, because that's going to be how you're very quickly going to be able to calculate your swipe distances. Thanks for listening.